system below it into a complete operating system. The services are divided into 4 major blocks, by broad functional area. Generic operating system services, communications services, multimedia and graphics services, connectivity services. Together, these provide technology-specific but application-independent services in the operating system. Among the other important frameworks and libraries found in this layer is the Multimedia Framework, providing framework support for cameras, still and moving image recording, replay and manipulation, and audio players, and the C Standard Library, an important support library for software porting. Java M.E. In some senses, Java does not fit neatly into the layered operating system model. Symbian's Java implementation is based around a virtual machine and layered support for the Java system which complements it, based on the MIDP 2.0 profile. A set of standard MIDP 2.0 packages. An implementation of the PLDC 1.1 language, I/O, and utilities services. A number of low-level plugins which implement the interface between PLDC, the supported packages, and the native system. Java support has been included in Symbian OS from the beginning, but the early Java system was based on Java and Java Phone. A standard system based on Java ME first appeared in Symbian OS 7.0 seconds. Since Symbian OS 8, the Java VM has been a port of Sun's CLDCHI. The Application Services Layer. The Application Services Layer provides support independent of the user interface for applications on Symbian OS. These services divide into 3 broad groupings. System-level services used by all applications, for example the application architecture or text handling. Services that support generic types of application and application-like services, for example personal productivity applications, vCard and vCal, alarm server, and data synchronization services. Also included are a number of key application engines which are used and extended by licensees, calendar and agenda model, as well as legacy engines which licensees may choose to retain. Services based on more generic but application-centric technologies, for example mail, messaging and browsing, messaging store, MIME recognition framework, HTTP transport framework. Applications in Symbian OS broadly follow the classic object-oriented model viewer controller, MVC, pattern. The framework-level support encapsulates the essential relationships between the main application classes, representing the application data model, the views onto it, and the document and document user interface that allow it to be manipulated and persisted, and abstracts all of the necessary underlying system-level behavior. In principle, a complete application can be written without any further direct dependencies, with the exception of the user library. The application services layer reflects the way that the system as a whole has evolved. On the one hand, it contains essential application engines that almost no device can do without, the contacts model for example, as well as a small number of application engines that are mostly now considered legacy. On the other hand, it contains, from Symbian OS 9.3, the SIP framework, which provides the foundation for the next generation of mobile applications and services. A framework layer. The tipmost layer of Symbian OS, the UI framework layer provides the frameworks and libraries for constructing a user interface, including the basic class hierarchies for user interface controls and other frameworks and utilities used by user interface components. The UI framework layer also includes a number of specialist, graphics-based frameworks which are used by the user interface but which are also available to applications, including the animation framework, the front-end processor, FEP, base framework and grid. The user interface architecture in Symbian OS is based on a core framework called Yukon and a class hierarchy for user interface controls where it is clear, it is not clear how to make a profit from what it replaces them with. The system model is relatively constant across different releases, although its details evolve to track the evolution of the architecture. Called the control environment. Together, they provide the framework which defines basic GUI behavior, which is specialized by a concrete GUI implementation, for example, S60, UIQ or MOAP, and the internal plumbing which integrates the GUI with the underlying graphics architecture. Icon was originally created as a refactoring of the Icon user interface library, which was part of the earliest versions of the operating system. Icon was created to support easier user interface customization, including pluggable look and feel modules. Next, let's consider about the file system of the Symbian operating system. On a Symbian smartphone, the file system can be accessed by means of the file server component, also referred to as F32, which manages every file device. It provides services to access the files, directories and drives on those file map devices. The file server uses the client-server framework by receiving and processing file-related requests from multiple clients. Moreover, it is able to deal with different file system formats, such as the FAT format used for removable disks, by using components that are plugged into the file server itself. In addition, it supports a maximum of 26 drives, each identified in DAS-like convention by a different drive letter, in the range A to Z. The main ROM drive, where the firmware resides, is always designated as Z. This drive holds system executables and data, which are referred to as XIP, executable in place, because they are directly launched without being loaded into RAM. Besides this, the firmware, or RAM image, is usually programmed into flash memory, known also as EEPROM, the non-volatile memory that can be programmed and erased electronically. The C drive is always designated as the main user data drive, which can be mapped onto the same flash memory chip of the firmware, whereas any removable media device is generally designated as D or E. It is worth mentioning that every access from a client to file server takes place via a file server session, by means of RF server session class, which implements all the basic services to interact with the file system. So far, we can obtain information about drives and volumes, act on directories, obtain notification about the state of files and directories, analyze file names, verify the integrity of the file system, and finally, manage drives in file systems. About the architecture of Symbian operating system. Next, let's pay our attention for the architecture of Android operating system. Android OS architecture. The architecture is based on Linux 2.6 kernel. Linux kernel is used as a hardware abstraction layer. Reason for using Linux is because it provides a proven driver model in a lot of cases ingesting drivers and also provides memory management, process management, security model, networking and a lot of cooperating systems infrastructures that are robust and that have been proven over time. So now let's consider about the system architecture, which consists of libraries, runtime environment and application framework. The next level up is native libraries. Everything that you see here is green is written in C and C++. At this level where the lot of core power of Android platform comes from. Let's consider what these components are. We'll start with the Surface Manager. The Surface Manager is responsible for composing different drawing surfaces onto the screen.